Hello everybody! Welcome to Creating the Basic Adaptable Game Engine Library, Part 32, Physics Theory. So we're still working towards Starfish Collector version 2.0. One of the things you might have noticed about the original game is that the turtle, as we move it around the screen, starts very suddenly and stops very suddenly. It's very responsive to the controls, but to be slightly more realistic, we should have the turtle slowly build up speed until it gets to some maximum speed, and then when we let go of an arrow key, it should slowly slow down until the turtle stops. So the goal of this and the next few videos is to implement that feature by simulating some very basic physics. So before we write some code, we should talk about physics, starting with talking about velocity. Now, velocity represents a change in a position. And since this is a two-dimensional game, each position has x and y coordinates, so we have to store how much the position is going to change in both the x and y coordinates. For that reason, we'll store velocity as a vector. The speed of an object is actually the same as the length of the velocity vector. Right? The more you're changing in each direction, the longer that vector will be. In addition, the angle of motion of a sprite moving across the screen can be defined as the angle of the velocity vector. So to talk about what these formulas would include, let's say P represents the position vector with components P1 and P2. Let's say V represents the velocity vector with components V1 and V2. And we'll follow mathematical tradition and we'll use the variable dt to represent delta time. And delta is commonly used in physics to represent the change in some quantity. And so delta time, you can think of that as the change in time since the last time position was updated, or the elapsed time since the previous frame of our game loop. If you've taken calculus, you don't need calculus, but if you have, you've probably seen an equation like this, dp dt equals v. What this is saying is that the change in position with respect to time is defined to be exactly the velocity. And the units for velocity, we'll think of those as pixels per second. Now I could take this equation and rearrange it a little bit. Informally, multiplying both sides by dt, we'll end up with the equation dp equals v times dt. And here, since d, or delta, represents change, dp represents change in position. So to calculate the change in position, you'll multiply the velocity times the change in time. And so for example, if your velocity is 100 pixels per second, and 1/10 of a second has gone by, well then your change in position would be 1/10 of 100 pixels per second. In other words, that would be a total change of 10 pixels. And here, in gray, these are the units for this calculation. dp, the change in position, that's some amount in pixels. And we can think of that as the velocity, measured in pixels per second, times the fractional number of seconds that have gone by. So the units also lined up. Then, once we calculate the change in position, what we need to do is increment the position by that change. And to see how that would work in code, basically we'll take each component of position and add or increment it by the velocity multiplied by dt. So p1 plus equals v1 times dt, and p2 plus equals v2 times dt. And that's how the velocity calculations will go. But in addition to velocity, to get that slowly speeding up and slowing down effect, we need to talk about acceleration. Now, acceleration is to velocity what velocity is to position. Acceleration represents a change in velocity. And since velocity is a vector, Acceleration is also stored as a vector. Now in this case, the length of the acceleration vector, I'm not sure if that has a standard name. We'll just call that the acceleration value. And often when we move sprites around the screen, what we'll do is we'll accelerate by whatever this value is, by this amount in a given direction. So in our physics class, which we'll create later on, we'll store a base acceleration value, and then we'll accelerate in the direction of an arrow key by that amount. Now, the calculations for acceleration are, again, extremely similar to the ones for velocity. In fact, if I switch between these two slides, you can maybe see that there's very little change in these formulas. To calculate the effect of acceleration on velocity, assuming v represents velocity, the vector with components v1, v2, and if a represents acceleration, the vector with components a1 and a2, well, change in velocity over time is precisely acceleration. That's how we're defining acceleration. The units for acceleration, in our case, will be pixels per second squared, or in other words, pixels per second per second. Now, what that means is when some amount of time goes by, some amount of seconds, there will be some change in velocity. The number of pixels per second will change. I'll do an example in just a moment. Rearranging this equation, we get the change in velocity, right? dv represents change in velocity, equals the acceleration times the change in time. So as an example calculation, let's assume your acceleration was 200 pixels per second. You're accelerating relatively fast. And if your acceleration is 200 pixels per second and a quarter of a second goes by, right, how much should the velocity change? Well, if acceleration was 200 pixels per second and a quarter of a second goes by, that means a quarter of that acceleration is applied to velocity. Right? 200 times 1/4 would be 50. So your velocity would increase by 50 pixels per second over the course of that quarter second. Just like the calculations for position, the change in velocity, the components v1 and v2 will be incremented by the acceleration components, each multiplied by delta time, the change in time. Now, there's two other considerations we'll need to keep in mind before we write the physics class. We'd also like to consider deceleration. Right? As long as you're holding down one of the arrow keys, you're going to start accelerating, but what happens when you let go? In this case, we'd like to gently slow down, and that's called deceleration. Right? We'll only apply this when we're not accelerating. So it's not a perfect physics simulation, but it will be good enough for our purposes. So deceleration will be some reduction in speed, and you can think of that as simulating some kind of a force like friction or wind resistance, or in this case of a turtle swimming, water resistance. We also want to keep in mind the speed. Right? The speed is a positive quantity, so it's always at least zero. You can't have negative speed, but we should also set some kind of a maximum speed. If we don't, then in theory our sprites could accelerate to any arbitrary speed, or as I like to think of that, glitch speed. Right? If you accelerate quickly enough, then in a single frame, in a single 60th of a second, you might be moving fast enough to pass through solid objects, or pass, across the entire screen in just a moment. And we typically don't want that to happen. So we will set and enforce some kind of a maximum speed. And finally, with all this information in mind, here's how the physics updating algorithm will work. It will require a bunch of information to be stored, like position, velocity, and acceleration. And the first step will be to increment the velocity according to the acceleration. Next, we'll have to make sure that the velocity, and specifically the speed, is within the boundaries we set. So first, we can extract the speed from the velocity. That's the length of the velocity vector. We'll decelerate if we're not accelerating. And then we need to check the speed bounds. Right? We're subtracting something from the speed. We need to make sure it didn't go below 0. And if we're accelerating, we need to make sure it did not go above the max speed. If it goes out of those boundaries, we need to set it back to a value within these boundaries, from 0 to max speed. Once we've determined what the speed should be, we'll reapply that speed to correct the velocity if we need to, and then we'll increment the position according to the velocity. When it's all done, we'll reset the acceleration back to 0. Right? This last step you can think of as if you drive a car, for example. In order to accelerate, in order to keep moving, you have to keep pressing that acceleration pedal down. If you just tap it once with your foot, all the acceleration is kind of used up in a single application. Right, so when we later move our characters across the screen, as long as we're holding down those movement keys, we'll have to continue applying acceleration. But the update algorithm will reset it every time. It'll get kind of used up. All right, that's basically how physics is going to work in our game. In the next video, we'll talk a little bit more detail about how the physics class itself will be set up. But this is a good stopping point for now. Thanks for watching.